rock and roll. How much? Right. Try not. If you did this example and don't try not to go back to it. Needed. 454 grams of solid atomic aluminum. If the reaction feeds at 78%. To give you a little bit more information, for practice, you have covered enough information at this point to do it with the information that I put on the whenever you're producing a solid metal, it's just going to be in an atomic state, or it's just going to be Al. It won't be Al2, Al3, Al4. You're getting solid aluminum, it'll just be Al. Where do we start? She did the first step for you. Chemical formula. We probably figure out what aluminum trioxide is. Anybody want to take a stab at how we go about determining that? Not necessarily what it is, because I remember that, but how are we going to go about determining that? Julia? So the ionic formula for aluminum trioxide, how are we going to come up with that if you're not given it? So it would be fair game for on the test to say, produce the ionic formula for aluminum trioxide. Any idea how we would go about it? What if I asked you what's the ionic formula for calcium chloride? Any thoughts on how you go about doing that? No? So calcium CH chloride is Cl. As a review, anybody remember what NiHide, right?
Iodide is a metal and non-metal. I know there's a specific word for it, but that's how I'm thinking of it. So iodide is metal and non-metal.
Iodide will be your monoatomic ion. How it doesn't necessarily mean you only have one chloride, but however many of them you have, you only have chloride. Right? So in this case, this would be Cl minus this ion. What about ice? What is ice? If I told you this was calcium chloride. Anybody want to take a stab at the difference between calcium chloride and calcium chloride? Where else do you remember seeing ice in H? favorite thing to remember, the polyatomic ion. So these are both polyatomic ions. Which one will have more oxygen, your ice or your H? Right. And so nitrite and nitrate, you have NO2 and NO3. Sulfite and sulfate, you have SO3 and SO4. So remember, as you go down the line, you can have hyper something ice, and that's something ice, that's something H, and per something H. And these are all increasing the number of oxygens. Doesn't necessarily mean that ice will always have 2 oxygens, and 8 will always have 3, but 8 will always be 1 more oxygen than ice, which is 1 more oxygen than hyper, whatever that comes with ice. So as an example, we can have COO minus. So that's hypochlorite when it's a polyatomic ion. So what would chlorite be? Julia? We are increasing our oxygen as we go down. COO2. Remember the charge doesn't change. The charge will always be the same regardless of the number of oxygen. Alex, how about chlorate? COO3. And perchlorate will be COO4. So I have chlorite, that would be COO2 minus. And chlorate would be COO3 minus. So those are your differences between your polyatomic ions, prefixes and suffixes. Over here, how to identify your ions. So for example, if you had to distinguish between calcium chloride, calcium chlorite, and calcium chlorate. We know that chloride will be Cl minus. Why do we know that this is -1? Alex, what's the name from? Great. We figured out a good. Remember that atoms are stable with 8 electrons. So you have something in this column on the left hand side. So having what happens? How do you roll this down? Well, what's the charge on an electron? -1. So if you're adding 1 negative charge, when chlorine becomes chloride, it would be at minus. When chlorine becomes chloride, it would be Cl. You can go down the line. We'll do a couple more examples. So how about calcium? What's the charge going to be on a calcium cation? Remember, cations and anions. Anions are your negatively charged ions, your cations are your positively charged. Calcium here, in the second group, and calcium has 2 electrons in its outermost shell. So if we were to think, is that closer to 0 or closer to 8? It's going to be closer to 0. It's going to give up 2 electrons. Because if you have calcium too specific, it's got a couple shells underneath. And the outermost one has got 2 electrons. Well, if it gives us those 2 electrons, now its outermost shell has 8. So there. And if you're giving up 2 minus charges, you would become more positive. Now, if we have the charges of our ions, how are we going to go about putting together the ionic formula? What's the trick? Cross it over, swap our charges for subscripts. We make sure that we are as reduced as possible. So we get CaCl2. Does that make sense to everyone? So we're going to do the same thing over here. So what does it mean when I say aluminum 3? Roman numeral here, aluminum 3. Alex? What's that? Plus 3. We have Al, 3 plus there. And we have oxide. So that means we're going to have oxygen. And what's the charge on oxygen when it becomes an ion? So once we know this, how do we come up with the formula for aluminum 3 oxide? We get Al 2 O3. Al 2 O3. And this aluminum oxide combines with atomic carbon. That's C. And I'll also tell you that this is probably and we know this is going to form CaCl plus CO2. Now, what do we need to do with this reaction before we go to the next step? What do we need to do? How? Balance it. Julia, Stephanie, I'm not sure. But what needs to happen here, remember, you set up your table with reactants and products. In this case, carbon is by itself. We're going to want to put carbon last because that'll be the easiest. And we have aluminum, oxygen, and carbon. Those are our 3 elements in this reaction. Now we go through and identify how many we currently have on the reactant side and the product side. So Julia, how many aluminum atoms do we have on the reactant side? 2. How about oxygen? 3. And carbon? 1. Alex, how about the product side? What do we have? 1, 3, 1. Right, so first, we want to balance our aluminum. So we've got 2 on the reactant side, 1 on the product side. Go in and put it together. Aluminum is by itself, so it doesn't change. Hindsight, we could have put oxygen above aluminum, but we also have aluminum by itself. Aluminum is balanced, and we go back down to oxygen. We have 3 oxygen over here, and 2 oxygen over there. We're going to need to add a coefficient here. We want to pick one that works on both sides. We have units of 3 oxygen here and units of 2 oxygen there. So what is your common factor of 3 and 2? What is something that is divisible by both 3 and 2? So we're gonna want to end up with 6 total oxygen. And we could play the game where we go 1 here, well then we're gonna have to go over here and put a 1 here, and then go back to the 2. We know that our lowest common factor is 6. So what do we need to put here to get 6 oxygen? 3. 3 there, we have the 6 oxygen. What else do we change? 3 carbon, no. And so now we can go back to the other side. I'll have to put a 2. Now our oxygen is balanced, but we store aluminum. So how many aluminum do we have on the reactant side? 4. We go back to the product side here with our aluminum. 4. Now our aluminum is balanced, our oxygen is balanced. The last thing we need to do is balance our carbon. Here. And everything is balanced. And we can go through and double check to make sure we are as simplified as we can be. We can't divide out anything from our stoichiometric coefficient. So now we have a balanced chemical reaction. What is our next step? How much aluminum oxide, how much carbon are needed to prepare 454 grams of solid atomic aluminum and carbon dioxide if the reaction exceeds 78%. So, we want to prepare 454 grams of aluminum. 454 grams of aluminum. As a general rule, whenever you're dealing with these types of problems, your first step is always a good bet to determine the chemical equation and any one. You guys haven't gotten much mathematics formulas yet, but first step, determine the chemical equation. Second step, always convert to moles. These steps will always work. Determine what your chemical equation is, and convert what you have to moles. We have 454 grams of aluminum. How do we go about converting that to moles? 454 grams of How do we go from grams to moles? Molar mass. How do we find the molar mass of aluminum? W. You're down with the table. 26.98. Today we'll just say about 20. On to test. I would recommend point out just a couple of decimals for everything except 27 grams of aluminum and 1 mole of aluminum. So our grams would cancel, and we'd be left with moles. Series. 454 divided by 27. We get 16.18. Moles of aluminum. 16 moles. How do we go from moles of aluminum in the product side to knowing how many reactants we need on the reactant side? Yeah, moles. So we have our stoichiometric coefficients. Right? Do you understand what those mean conceptually? So we have two compounds of aluminum oxide. We're going to need 3 atoms of carbon to help it, to make this reaction proceed. Everybody good there? So aluminum, we're going to make 4 aluminum for every 2 aluminum oxide that we have. So if this reaction were to proceed efficiently at 100% yield, what's that mean? Going from 2 to 4. What does that mean? Doubling, right? So if we're making 16, how many must we have started with? So we can draw this out with dimensional analysis. I have 16 moles of aluminum, and I know that for every 2 moles, for every 4 moles of aluminum, we need 2 moles of aluminum oxide. Our moles of aluminum will cancel, and we can multiply through to get 8 moles of Al2O2. So this is if this reaction were to proceed at 100% yield, but we're not. We're at 78% yield. Mathematically, it's pretty easy to determine this. I'd like to with that form of dimensional analysis. Okay, so what is that 78%? Does anyone want to take a stab at what we need to do to get our final answer for aluminum oxide to account for that 78%? So we're going to say this is 8 moles of aluminum oxide that we put into the reaction. We want to basically react 8 moles. If we react 8 moles, we're going to produce 16 moles of aluminum. Does that make sense? Kind of, sort of. It might make more sense once we just do the math of it, but I want to be consistent with the dimensional analysis. So we also know that if we put a 78% yield, what does that mean? If I put 100 grams in, or 100 moles in, I'm only going to get a yield of 78 moles back. Does that make sense? Yes. If I buy ingredients to make 100 cupcakes and I mix them all together and I can only make 78 of them, I have a 78% yield. So we have 100 in, 100 moles in, 78 moles out. That, for those of you that just want to see it mathematically, you have 8. We're going to divide it by 0.78, which is the decimal form of your 70%. Before you do that, you could take a step back and say, could this number get bigger or smaller? Any thoughts? Could this number be bigger or smaller? So if I have a reaction that proceeds at a 90%, and I have a second, the same reaction but under different conditions, it proceeds at a 60%. Which one am I going to need more reactive to produce the same number of products? 60%. Because that's less efficient. So I need to start with more to get to the same amount less. Does that make sense to everyone? So we know this number should get bigger. So if you were to multiply times 0.78, you know you're going to be smaller. Then you divide by it. Divide by 0.78. I don't know what we get. Divided by 0.78. 10.26-ish. Now we need to do the same thing for our carbon. So just like we did previously, I want you guys to try to work on your own to determine how many moles I need to start with carbon to produce the 454 grams of lead. You guys ready to go through it? Alright, follow the room, here we go. So, if we're assuming that we have 16 moles of aluminum, and we already calculated that, we don't have to go all the way back to the front. We already know how many moles of aluminum we have. And once we get into the moles, we can do a lot more with it. 16 moles of aluminum. And we know, based on our balanced reaction, that for every 4 moles of aluminum that we produce, we need 3 moles of carbon. So right now we've got moles of aluminum in the numerator. We're going to want moles of aluminum in the denominator. So aluminum cancels. We're going to put moles of carbon up top. If we do that, we would get 12 moles. But remember, you have to account for the 78% yield. And we multiply this times 1 over 0.78 or 100 over 78, whichever way you want to think of it. Divide by that percent yield. And we're going to get
16. Yeah, I got like 16.
15 moles of carbon. Any questions on this problem? You get a lot of big important concepts. I know it took a lot of time, but between reviewing your polyatomic ions and your other ions and yields and balancing chemical reactions, we hit a lot of important concepts that you guys should be reviewing. Any questions on this? Okay. You're all masters of this now? Yeah.
I didn't have a novel before.
One step at a time. All right. All nice. I want you to try to get back in your memory and come up with the ionic formulas for each of these ionic compounds. Try to do it from memory if you need the reference stuff. I'm going to stop you, but I want you to try to come up with it as though it's a quiz worth million points. I'm going to do a lot of stuff. finish with this example, which is combining several different things. So it'll be another one of those complex problems where you can draw on different concepts that you talked about. All right, who's got calcium phosphate?
And the atoms from that goes
Nope. CO42. So calcium is plus, phosphate number 3 minus. Phosphate means CO4 3 minus. With your charges, make sure it's simplified. Oh, about aluminum hydroxide. I'm sorry, ammonium hydroxide. H4OH. Ammonium plus 1, hydroxide minus 1. When those come together, we get H4OH. Oh, about sodium sulfite. Any thoughts on sodium sulfite? And the sodium's got plus 1. Sulfite is SO3 2 minus. NO2 SO3. Right? And down the line, magnesium nitrate. Anybody have magnesium nitrate? NO3. We know that nitrate is NO3 minus. Magnesium, the ion is Mg2 plus. With your charges, we get MgNO3 2. All about manganese 4 sulfide. Why not Mn2x4? Well, here we're going to set plus 4. Sulfide is minus. Why not Mn2x4? Alex? Right. Remember, with your ionic compounds, we want to simplify as far down as we can because these aren't discrete bonds. Right? They're just ratios between compounds. Any questions on this with each of these? Are any of these staying for bio? Do you mind if we might go over a little bit with this example again? Right. So, if you mix 5 milliliters of 10 molar hydrochloric acid with water to a volume of 100 ml, and mix 5 grams of calcium hydroxide with water to 50 ml, and mix the solutions, how many grams of calcium chloride do you produce? So, a little bit of a tricky problem. We have several steps here. First off, what do we do? Well, we've got 5 ml of 10 molar hydrochloric acid. Everybody know the formula for hydrochloric acid? Oh. HCl. Remember, if it's hydro something it, it's just the ion, there's one of the polyatomic ions there. So HCl. And we're adding that to 100 ml, the total volume of 100 ml of water. So, how do we determine the resulting concentration? Well, you could reason through it, right? We are diluting it by a factor of 20. We're going from 5 ml to 100 ml. So probably going to have 1/20th of the concentration. But as a general rule, you've got P1, V1 equals P2, V2, which you will see very, very soon if you haven't yet. So what this tells us, we also make the M1, V1 equals M2, V2. So our concentration times our volume will be equal on both sides. And so our first concentration is 10 molar. Now, because we have things equal to each other, as long as your units are the same on both sides of the equal sign, you're okay. You don't need to convert into SI units. It's helpful to, you can, but the biggest thing is going to be to make sure that your units are the same on either side. We have 10 molar times 5 mil, and that's going to be equal to 100 molar, 100 mil times an unknown concentration. It's all correct. We end up, like we said, at 1/20th. We end up with X equals 0.5 molar. 0.5 molar. So we know we have 100 mils, 0.5 molar of HCl. Our next step, we mix 5 grams of calcium hydroxide with water. 50 mils. And we got 5 grams. What's the ionic formula for calcium hydroxide? What's hydroxide? That's an OH minus. What's the charge on calcium when it becomes ion? So Ca plus, we flip our charges. We have CaOH2. CaOH2. Well, we've got grams. So what are we going to do to get grams of concentration? You got to convert it to moles. Always convert to moles. Because remember, molarity by molar is moles per liter. So we've got to get to moles. How do we convert 5 grams of calcium hydroxide to moles? Molar mass. A theory. What's the molar mass of calcium hydroxide? 73.97. So we get 73.97 grams in 1 mole. Right? Yep, we can do it all right here. So now we have moles on top, and remember molarity equals moles per liter. We already have moles on top. We need to get liters in the denominator. What's our total volume? 50 mils. So how many liters is that? So we've got 50 milliliters. And we know that there are 1,000 mils in 1 liter, or 10 to the third. We would get 0.05 liters. Somebody want to calculate this?
1.35.
1.35 molar solution. We have 50 mils of 1.35 molar CaOH. Right? We've got our concentration. Now, any ideas on what we should do next? One of those two steps that I said you should always do. You really already done the second step. Determine your chemical station. So, we are mixing hydrochloric acid with calcium hydroxide. What are we going to make? Chemicals is what we're making. The question. But remember, your positively charged species are going to go with the opposite negatively charged, otherwise we're going to make the same stuff. So we end up with the H going with the OH, and the Ca with the Cl. We end up with calcium chloride, Ca2 plus, Cl minus, bring together, switch your charges, and water. This is a Bronsted-Lowry acid-base reaction. Now we want to make sure we balance. We want to make sure that we balance. This, you guys are good at feeling this, but right now this is HOH. So if we go through and balance this, we have H, Cl, and OH. Because this is such an ionic reaction, we are okay to put the ions in the middle column because those aren't being broken up throughout the reaction. So how many H do we start on the product side and the reactant side? One. There's H left. That's what's a little tricky. Cl. Oh, Ca, 1, and OH, 2. Alright? And give them enough to join some bile. I'll talk through this, but I'll go through and work through it. So on our product side now, we have 1 calcium, 2 chloride, 1 proton, and 1 hydroxide. We can go through and balance. Right now, our protons are balanced, but chloride is not. I'll become 2 here, this will become 2, but I also changed the number of hydrogens. So now I've got to put a 2 over here on my water to balance that. In the meantime, we balance our OH, we are good to go. We're nice and balanced, just like that. Now we're balanced. So, we have concentration. Do concentrations really matter all that much right now? No. What we really care about is how many moles of these things that we have. How many moles that we have. So we could have stopped one step earlier in our calculations to leave it at moles, or we can go ahead and convert this. So 100 mils is 0.5 molar. That would mean that if we had 1 liter, we would have half a mole. We have 1/10 of a liter, so we have 0.05 moles of HCl, 0.05 moles of HCl. You can go through and dimensionally analysis work it out. 50 mils of 1.35 molar. So we would have 1.35 moles if we had a liter. We have 1/20th of a liter. So we would take 1/20th of that. 1.35 divided by 20.
0.0675.
0.675. Now we have to determine what our limiting is. Okay. So this is how much we start with. Dr. Morgan may or may not teach it this way. Good thing is this, more technical stuff, it's good to apply what you've learned so far and really cement what will be on the exam. But unless you really get in depth this week, you don't need to have stuff like this. So this is often called ice or ice table. 0.5 and 0.05 and 0.0675. Change our coefficient, and we are removing it because it's on the rate minus x. Basically, we're putting this in units of the reaction. So this would have, for every one time this reaction occurs, we would need 2 HCl and 1 calcium hydroxide. And then we could solve 0.05 equals that. So actually be 0.0. Rather than dive into this right now, just think about it. So if I have 0.0675 moles of calcium hydroxide, how many moles of HCl would I need? We could set it up the same way we did the other one, where I've got 1 mole and 2 moles. I would put the 1 on the bottom, 2 on the top. I would need twice as much. Okay? Does that make sense? I would need twice as much. I don't have twice as much. Does that make sense? Whereas the HCl, I would need half as much calcium hydroxide. We have half as much. So what's going to be our limiting reactant? HCl. So we're going to do all of our calculations off of our limiting reagent. We have 0.05 moles. So that means we are going to create 0.05 moles of water, and because we have a 2 here and a 2 here. So that's what I calculated at 0.025. 1 unit of reaction multiplied times by 2. And we're going to make 0.025 moles of calcium chloride. We want grams, so we can go through and multiply that times the mass in theory. What's the molar mass of calcium chloride? 109.9. 2.6. So 2.74 grams. Fine. In reflection, this is a complex problem, but different components of it you know how to do. We just put it all together. It's chemistry. You should know how to calculate the concentration. You should know how to come up with what the ionic formulas are for these compounds, and likewise the balanced chemical reaction what you have with ionic formulas. Right, the specifics here, once you get into the reaction, that's the stuff you covered very recently on Monday and Tuesday with limiting reactant. But all of this is stuff that you have covered. You're just not as well stuck. Does anyone have any questions on what we covered this problem, what we covered all day, or general math and or chemistry questions? Nothing? Overwhelmed? Deep breath. Resistance on Tuesday and nothing make it Friday. No. All right. Good. Perfect. You always feel free to email me if you have any questions. If you want, stick around and give you my email. Otherwise, you guys have a wonderful night. Unless you're sticking around for biology, and then we'll talk about cells. Have you gotten to cells yet? Almost. Okay. All right, you guys have a good night. You're welcome. Want to talk about some biology? You want to go a little ahead of where you guys are right now? I'll show you in a second.